Right now, as you listen to this, you're racing through space at over 1 million miles per hour. Not because of Earth spinning or orbiting, because something massive is pulling our entire galaxy across the universe. Scientists call it the Great Attractor. A gravitational monster with the mass of tens of thousands of galaxies hidden behind a curtain we cannot see through. It's dragging the Milky Way, Andromeda, 100,000 other galaxies, all toward a destination we've never observed. If you enjoy unraveling cosmic mysteries, hit that like button and subscribe. What you're about to discover will change how you see our place in space. Prepare yourselves. We begin. In the 1970s, astronomers noticed something impossible. Every galaxy near the Milky Way was moving in the same direction. This shouldn't happen. When the universe exploded into existence 13.8 billion years ago, everything began spreading outward in all directions. Like a bomb detonating in slow motion, space itself stretches between galaxies, pushing them apart. Scientists call this cosmic expansion. The farther away a galaxy sits, the faster it should be, racing away from us. This is confirmed. This is measured. This is the foundation of modern cosmology. But something was wrong. Astronomers measured the light from nearby galaxies, looking for the telltale signs of motion. Light stretches when objects move away, shifts toward red wavelengths. Light compresses when objects approach, shifts toward blue. The data showed galaxies moving exactly as expansion predicted. Then they looked closer at the small deviations, the tiny differences in speed. Every galaxy in our cosmic neighborhood had extra motion layered on top of expansion, not random motion, not scattered in different directions. Directed motion, purposeful motion. Hundreds of galaxies, all being pulled toward the same point in space. Imagine standing in a field during a storm. Rain falls everywhere, blown by wind in random patterns. Then you notice something strange. Every raindrop near you, no matter where it starts, begins curving toward one spot on the horizon. Something over there has changed the rules. Something is pulling. The Milky Way itself was moving at over 600,000 miles per hour in a specific direction. Our entire local group of galaxies, including Andromeda and dozens of smaller companions, was being dragged along. The Virgo cluster, containing thousands of galaxies 60 million light-years away, was flowing in the same direction. The Hydra Centaurus supercluster, even farther out, was caught in the same current. Scientists checked their instruments. They recalculated. They measured again. The pattern held. Every measurement confirmed the same disturbing truth. Something out there, something massive beyond comprehension, was pulling on everything around us. The gravitational force required to accelerate thousands of galaxies across such distances would need to come from a concentration of mass, unlike anything they had ever detected. They pointed their telescopes toward the source. They found nothing. The region where all these cosmic rivers converged was hidden behind the densest part of our own galaxy. A wall of stars, gas, and dust blocked their view. They were trying to observe the greatest gravitational anomaly in the local universe while standing inside a cloud that obscured everything beyond it. But the pull was real. The motion was undeniable. Something was out there, invisible yet impossible to ignore, rewriting the rules of how galaxies should behave. Scientists needed a name for this mystery. They called it the Great Attractor. What could generate such enormous gravity remains one of the deepest puzzles in astronomy. The problem wasn't just that they couldn't see it. The problem was that the pull contradicted everything they thought they understood about cosmic structure. In the 1980s, astronomers believed they had mapped the major features of our galactic neighborhood. They knew about the local group. They had charted the Virgo cluster. They understood how gravity worked on large scales. Or so they thought. Then came the measurements that changed everything. Alan Dressler and his team began collecting data from galaxies across millions of light years. They measured redshift, the stretching of light that reveals how fast objects move away. They calculated distances using multiple methods, cross-checking every number. When they combined these measurements, they could map out what astronomers call peculiar velocities. These are the extra motions of galaxies, the speeds they have on top of cosmic expansion. Think of expansion as a river carrying everything downstream. Peculiar velocity is like a fish swimming against or across that current. The maps revealed something stunning. Galaxies weren't just moving randomly. They were organized into a flow pattern, like water circling a drain. The Milky Way was caught in this current, moving at 600,000 miles per hour toward a point in the constellation Centaurus. The local group accelerated alongside us. The Virgo cluster, containing over 1,000 galaxies, was flowing in the same direction at similar speeds. Even galaxy clusters, hundreds of millions of light years away, showed the same directional bias. Scientists calculated the mass needed to create such a gravitational pull. The numbers were staggering. You would need to concentrate tens of thousands of galaxies in one region. The combined mass would equal 10 million billion times what our entire galaxy weighs. This is confirmed through multiple independent measurements. The gravity is real. The motion is real. The source remains hidden. But here's what made it stranger. The Great Attractor wasn't pulling equally from all sides. Galaxies closer to it moved faster, as expected from gravity. But the velocity pattern suggested something more complex than a simple point of mass. The flow lines curved and twisted, hinting at structure within structure, concentrations within concentrations. Whatever was creating this pull had internal architecture astronomers couldn't map. They tried different wavelengths of light. Visible light couldn't penetrate the galactic dust. Infrared light showed some features, but remained too obscured. Radio waves passed through the dust more easily, revealing hints of massive galaxy clusters lurking in the forbidden zone. Every new observation confirmed the Great Attractor existed. Every measurement failed to reveal what it actually was. The astronomical community split into camps. Some believed it was a single, supermassive structure, perhaps the largest galaxy cluster ever discovered. Others thought it might be multiple clusters aligned along our line of sight, creating the illusion of one enormous concentration. A few suggested more exotic possibilities involving dark matter distribution or gravitational lensing effects. None could prove their theory. By the late 1980s, the Great Attractor had become the most famous unseen object in astronomy. It was pulling us across the cosmos at speeds that boggled the mind. It was massive enough to influence the motion of structures 1 billion light-years across. And it was completely hidden from view, locked behind the one region of sky we couldn't observe properly. The race was on to pierce the veil, but the tools needed didn't exist yet. Picture a river system from high above. You see thousands of streams and tributaries, all flowing downhill, merging and converging toward the ocean. Now imagine that river system spans 500 million light-years. The streams are galaxies. The ocean is the Great Attractor. This is cosmic flow, and mapping it revealed something far stranger than anyone predicted. By the early 2000s, new technologies allowed astronomers to measure galaxy velocities with incredible precision. The Cosmic Flows Project began charting the three-dimensional motion of thousands of galaxies in our corner of the universe. These weren't simple measurements. Each galaxy required careful distance calculations using multiple methods. Scientists measured the brightness of specific types of stars that always shine with the same intensity. They tracked how fast galaxies rotated and compared that to their brightness. They used every trick available to build an accurate map. The data poured in slowly. Each measurement took weeks or months. Each galaxy added one more point to the map. After years of work, patterns began emerging from the noise. The local group wasn't just falling toward the Great Attractor. It was part of a much larger flow, a cosmic river containing thousands of galaxy groups and clusters. The Virgo cluster, which we thought was a separate structure, was actually part of the same stream. The Hydra Centaurus supercluster, lying even farther out, was caught in the same current. Galaxy after galaxy, cluster after cluster, all moving in coordinated paths toward a common destination. Scientists created visualizations of this cosmic flow. The images looked like weather maps showing wind patterns, except these patterns spanned hundreds of millions of light years. Streamlines showed the paths galaxies followed as they fell through space. Colors indicated speed, with red zones showing the fastest motion and blue zones showing slower drift. The Great Attractor sat at the center, a red-hot point where all the streamlines converged. But the maps revealed something unexpected. The flow didn't stop at the Great Attractor. It continued beyond, following paths that stretched even farther into space. Some galaxies near the Great Attractor were moving faster than gravity from that region alone could explain. Something larger was pulling from beyond. The cosmic river didn't empty into a single ocean. It was part of an even bigger system, flowing toward structures astronomers hadn't yet discovered. Think of it like finding a creek in the forest. You follow it downstream, expecting to find a pond. Instead, you discover the creek feeds into a larger river. Then, that river joins an even bigger river. The scale keeps expanding beyond your initial understanding. Measurements showed that galaxies 300 million light-years from us were being influenced by the same gravitational architecture. At these distances, light takes 300 million years to reach Earth. We're seeing these galaxies as they were when dinosaurs first appeared. Yet even then, they were already caught in the current, already flowing toward the same gravitational basin. The Cosmic Flows data suggested we weren't just part of a cluster or supercluster. We were part of something vastly larger, a structure so immense that it challenged the theoretical limits of what should be possible. According to cosmological models, there wasn't enough time since the beginning of the universe for gravity to organize matter on such scales. Yet, here was the evidence, measured and confirmed across thousands of data points. The Great Attractor was just the beginning. The real story was much, much bigger. Astronomers have a name for the region that hides the Great Attractor. They call it the Zone of Avoidance. This isn't some mysterious cosmic barrier or exotic physical phenomenon. It's just dust and gas and stars. Our own galaxy, blocking our view like a wall we can never see past. And it covers roughly 20% of the entire sky we can observe from Earth. Here's why this matters. The Milky Way is a spiral galaxy, shaped like a flat disk with a bulging center. We live inside this disk, about 30,000 light-years from the core. When we look up or down, perpendicular to the galactic plane, we see through relatively empty space into the distant universe. Billions of galaxies stretch out in those directions, visible and measurable. But when we look along the plane, parallel to the disk, we're staring through the thickness of our own galaxy. Through billions of stars, through clouds of dust and gas that span thousands of light years, through material so dense that it absorbs light almost completely. The zone of avoidance sits exactly where the Great Attractor hides. This is confirmed. The direction all those galaxies are flowing toward, the point where millions of billions of solar masses should be concentrated, lies directly behind the thickest part of the Milky Way's dust lane. Scientists couldn't have picked a worse location if they tried. Dust doesn't just dim light, it blocks it entirely. Think of looking at a candle through a thick blanket. The blanket isn't just making the candle dimmer, it's preventing you from seeing it at all. The dust grains in our galaxy do the same thing to light from distant galaxies. Visible light, the kind our eyes see and optical telescopes capture, cannot penetrate more than a few hundred light years through the galactic plane. The Great Attractor sits 250 million light years away on the far side. Edwin Hubble first noticed this zone in the early 20th century. When he mapped galaxy distributions across the sky, he found them everywhere except along the galactic plane. Not because galaxies avoided that region of space, but because our view was blocked. He called it the zone of avoidance. The name stuck. For decades, astronomers simply worked around it, mapping the universe everywhere else and accepting this cosmic blind spot as an unavoidable limitation. But you can't ignore the Great Attractor. It's pulling on everything, influencing galaxy motions across hundreds of millions of light years. Understanding it became critical to understanding the large-scale structure of the universe. Scientists needed to see through the curtain. The problem was that visible light couldn't do the job. The dust that blocks visible light does something else interesting. It absorbs short wavelengths, like blue and ultraviolet light, more effectively than longer wavelengths like red and infrared. This is why the setting sun looks red. Earth's atmosphere scatters blue light away while red light passes through. The same principle applies on cosmic scales. Infrared light, with wavelengths longer than what our eyes can see, can partially penetrate galactic dust. Not completely, but enough to catch glimpses of what lies beyond. Radio waves, even longer than infrared, pass through dust almost as if it isn't there. These wavelengths reveal a completely different universe, one where the zone of avoidance becomes transparent. Starting in the 1990s, astronomers began using radio telescopes to map the hidden region. They detected galaxies no optical telescope could ever see. They found massive clusters lurking in the forbidden zone. They started building a picture of what had been invisible for over a century. What they discovered in that darkness would force them to redraw their maps of the cosmos. The first radio surveys of the zone of avoidance revealed thousands of galaxies that were completely unknown. Not dim galaxies, not distant galaxies, massive galaxy clusters sitting relatively close by, hidden behind the curtain. Some were closer to us than well-known structures in other parts of the sky. We had been living next to cosmic giants without knowing they existed. Radio telescopes detect emissions from neutral hydrogen gas, the most common element in the universe. Every galaxy contains vast clouds of this gas, and it radiates at a specific frequency that passes through dust without being absorbed. By tuning radio receivers to this frequency, astronomers can map galaxies regardless of how much dust blocks the view. The technique is called HI mapping, named after the spectral line of neutral hydrogen. In 1996, a team using the Parkes Observatory in Australia began a systematic survey of the zone of avoidance. They called it the Parkes HI Zone of Avoidance Survey. The telescope swept across the sky night after night, collecting radio signals from the hidden region. The data revealed structure after structure, galaxy clusters containing hundreds of members, filaments of galaxies stretching across tens of millions of light years, superclusters that rivaled anything found in the visible parts of the sky. One discovery stood out. A massive concentration of galaxies appeared exactly where the Great Attractor was predicted to be. The Norma cluster, sitting 220 million light-years away, contained thousands of galaxies packed into a relatively small volume of space. This is confirmed. The cluster's mass could be calculated from the velocities of galaxies within it. The numbers matched predictions for part of what was pulling on the Milky Way, but only part. The Norma cluster was enormous by any standard. Thousands of galaxies, each containing hundreds of billions of stars, all bound together by gravity. Yet its mass wasn't enough. To generate the pull observed on galaxies across hundreds of millions of light-years, you would need multiple clusters working together. The Norma cluster was the centerpiece, the most massive single structure in the region. But it was part of something bigger, a concentration of multiple clusters and superclusters that combined to create the Great Attractor's gravitational influence. Astronomers also found the Great Attractor Wall, sometimes called the Norma Wall. This is a massive filament of galaxies, a cosmic structure spanning over 100 million light-years. Imagine a highway of galaxies, billions of light-years long, connecting different parts of the universe. The Norma Wall forms one of these highways, running through the zone of avoidance. It contains multiple galaxy clusters, including the Norma cluster and others with equally impressive masses. Think of it like discovering a mountain range that was always there, hidden by fog. As the fog clears, you don't see one mountain. You see dozens, connected by ridges and valleys, forming a system far more complex than a single peak. The Great Attractor wasn't one thing. It was a region, a concentration of structures, a node where multiple cosmic filaments intersected. The radio surveys revealed something else. The density of galaxies in the zone of avoidance matched the density everywhere else in the universe. The zone wasn't special in any physical sense. It only seemed empty because dust blocked optical observations. Once astronomers could see through the dust, they found the same types of structures, the same types of galaxy clusters, the same cosmic web that existed everywhere else. The universe behind the curtain looked exactly like the universe we could already see, except for one crucial difference. The structures hidden in the zone of avoidance were positioned perfectly to explain the motions astronomers had been observing. The Norma cluster and its companions weren't just random collections of galaxies. They were the gravitational engine driving the cosmic flow, pulling thousands of galaxies across millions of light-years of space. But even as these discoveries solved part of the mystery, they raised a bigger question. If the Great Attractor was this massive, this influential, what else might be hiding in regions we still cannot observe? The Parkes telescope wasn't the only instrument peering through the dust. By the early 2000s, multiple observatories joined the hunt, each using different techniques to probe the forbidden zone. The results built a three-dimensional picture of the hidden structures, revealing not just what was there, but how these structures fit into the larger cosmic web. X-ray observations added another layer. Hot gas between galaxies emits X-rays, radiation with even shorter wavelengths than visible light. You might think X-rays would be blocked even more effectively than visible light, since dust absorbs short wavelengths better than long ones. But X-rays have so much energy that they can punch through dust that would completely block visible light. Space-based X-ray telescopes like Chandra and XMM Newton scanned the zone of avoidance, looking for the telltale glow of hot gas in galaxy clusters. They found exactly what they expected. The Norma cluster blazed in X-rays, its hot gas reaching temperatures of tens of millions of degrees. This gas fills the space between galaxies, heated by the energy of countless stars and supernovae. The X-ray brightness revealed the cluster's mass with high precision. Combined with optical data from infrared telescopes and radio data from HI surveys, astronomers could calculate the total mass of the Great Attractor region down to reasonable margins of error. The number that emerged was shocking. Earlier estimates had suggested the Great Attractor might contain the mass of 100,000 galaxies. New measurements showed those estimates were too high by a factor of 10. The actual mass was only about 10,000 galaxies worth. Still enormous, still capable of generating significant gravitational pull, but not nearly as massive as originally thought. This created a new problem. If the Great Attractor wasn't as massive as expected, what was pulling so strongly on galaxies even farther out? The velocities astronomers measured required more mass than the Norma region contained. The numbers didn't balance. Something was missing from the equation. The answer came from looking beyond the Great Attractor. Telescopes mapped galaxy positions and motions even farther into space, past the zone of avoidance, into regions where observations were clearer. What they found changed everything astronomers thought they knew about our cosmic neighborhood. 650 million light-years away, beyond the Great Attractor, beyond the zone of avoidance, beyond all the structures they had been studying, sat an even larger concentration of galaxies. The Shapley supercluster, discovered decades earlier by astronomer Harlow Shapley, was the most massive structure in the local universe. It contained tens of thousands of galaxies, far more than the Norma region. And it was pulling. The Milky Way wasn't just falling toward the Great Attractor. It was falling toward the Shapley supercluster beyond it. The Great Attractor was like a stepping stone, a waypoint on a much longer journey. Think of rolling a ball down a hill. You focus on the valley directly ahead, but you don't realize the valley itself sits on the slope of an even bigger mountain. The Great Attractor was the valley. Shapley was the mountain. This revelation forced astronomers to rethink everything. The peculiar velocities of galaxies in our region weren't just caused by local structures. They were caused by gravitational influences extending across nearly 1 billion light-years of space. The cosmic flow patterns they had been mapping were part of a much larger system than anyone had imagined. Radio telescopes, X-ray observatories, and infrared surveys had pierced the zone of avoidance. They had revealed the structures hidden there. But in solving one mystery, they had uncovered another far grander in scope. The Great Attractor wasn't the final answer. It was just the beginning of understanding how our little corner of the universe fit into the bigger picture. And that bigger picture kept getting bigger. When astronomers finally got a clear view of the Norma cluster, what they saw both confirmed their theories and raised new questions. This wasn't just a collection of galaxies loosely bound by gravity. It was a dense dynamic structure containing thousands of members, each rushing through space at speeds that told stories of cosmic violence and gravitational chaos. The cluster sits at a distance of 220 million light-years. Light leaving the Norma cluster today began its journey when the first flowers appeared on Earth. When we observe it, we're seeing it as it was during the Triassic period, long before dinosaurs dominated the planet. Yet even at that ancient time, captured in the light now reaching our telescopes, the cluster was already massive, already ancient, already the gravitational anchor for surrounding structures. Galaxies in the Norma cluster move at speeds exceeding 1,000 miles per second relative to each other. They're not moving randomly. They're orbiting the cluster's center of mass, held in gravitational embrace by the combined pull of all the other members. Some galaxies are plunging toward the core for the first time, accelerating as they fall deeper into the gravitational well. Others are veteran members, having completed multiple orbits over billions of years, their trajectories shaped by repeated close encounters with other cluster members. Think of a swarm of bees around a hive. Individual bees move in seemingly chaotic patterns, but the swarm as a whole maintains structure and organization. The Norma cluster works the same way, except each bee is a galaxy containing hundreds of billions of stars, and the entire swarm spans millions of light years. The most massive galaxies in the cluster sit near the center. These are elliptical galaxies, shaped like footballs or spheres rather than flat spirals like the Milky Way. They grew to enormous sizes by consuming smaller galaxies over billions of years. Every time a smaller galaxy wanders too close, tidal forces rip it apart, and its stars join the growing elliptical giant. The largest members of the Norma cluster have masses equivalent to hundreds of Milky Way galaxies. They're gravitational monsters, dominating the cluster's core. Between the galaxies lies hot gas, so thin it would count as a near-perfect vacuum by Earth standards, but so vast that it contains more mass than all the visible stars in all the cluster's galaxies combined. This gas reaches temperatures of 50 million degrees Fahrenheit, hot enough to strip electrons from atoms and emit powerful X-rays. The gas glows brightly in X-ray observations, revealing the cluster's gravitational potential in stunning detail. But there's something even more massive hiding in the Norma cluster, something that generates more gravitational pull than all the galaxies and all the hot gas combined. Dark matter. This invisible substance doesn't emit light, doesn't absorb light, doesn't interact with anything except through gravity. Scientists know it exists because galaxies in the cluster move too fast to be held together by the gravity of visible matter alone. The cluster should have torn itself apart billions of years ago. Something invisible is providing the extra gravity needed to keep it bound. Calculations suggest dark matter makes up 85% of the Norma cluster's total mass. The galaxies we see, the hot gas we detect, all the normal matter combined, accounts for just 15%. The cluster is mostly invisible, mostly unknown, mostly made of something science cannot directly observe. Yet it dominates the gravitational landscape, shaping how galaxies move and determining the structure's long-term evolution. The Norma cluster sits at the heart of the Great Attractor region. It's the largest single concentration of mass in that part of space. But it doesn't work alone. Other clusters surround it, each containing hundreds or thousands of galaxies. Together, they form a supercluster, a cluster of clusters, a gravitational architecture spanning 100 million light-years. This is what was hidden behind the zone of avoidance. This is what pulls on the Milky Way with such relentless force. But as massive as the Norma region is, as impressive as these numbers sound, the story doesn't end here. Try to picture 10,000 galaxies. Each galaxy contains roughly 100 billion stars. Each star is enormous compared to planets, but tiny compared to the vast distances between them. Now, compress all of those galaxies into a region of space just a few 100 million light-years across. The resulting gravitational field warps space itself, creating what physicists call a gravity well. Imagine space as a rubber sheet stretched flat. Place a bowling ball on it, and the sheet curves down, creating a depression. That depression is a gravity well in 2 dimensions. In reality, gravity wells exist in 3 dimensions, curving space in all directions simultaneously. The Great Attractor creates one of the deepest gravity wells in the local universe. Any galaxy near it begins sliding down the slopes of that well, accelerating as it falls deeper. The Milky Way sits on the outer edge of this well. We're falling, but slowly compared to galaxies closer to the center. Think of a marble rolled across a tabletop. When it reaches the edge of a bowl sitting on the table, it doesn't immediately drop to the bottom. First, it circles the rim, gradually spiraling inward. That's where we are, on the outer rim, circling slowly while deeper regions pull with ever-increasing strength. But here's what makes the Great Attractor's gravity well unusual. It's not symmetrical. In a perfect gravity well, matter pulls equally from all directions toward a central point. The Great Attractor's well is elongated, stretched along certain axes, compressed along others. This asymmetry reveals the structure's composition. Multiple clusters contribute to the gravitational field, each adding its own distortion. The resulting well has ridges and valleys, fast lanes and slow lanes, regions where gravity pulls harder and regions where it pulls softer. Galaxies falling into this well don't fall straight down. They follow curved paths, spiraling inward while also moving sideways, creating complex three-dimensional trajectories. Some approach from one direction, others from another. The paths interweave like threads being woven into fabric. Over billions of years, these galaxies will converge at the bottom of the well, where the densest concentrations already exist. The mass of tens of thousands of galaxies generates measurable effects on light passing through the region. Gravity bends light, a phenomenon Einstein predicted and observations confirmed. When light from distant galaxies travels through the Great Attractor region, it curves around the massive structures there. This gravitational lensing effect distorts background galaxies, stretching them into arcs and sometimes creating multiple images of the same object. Astronomers use these distortions to map the distribution of mass, including dark matter, throughout the region. Think of looking through an old glass window with waves and imperfections inner it. Objects on the other side appear warped and distorted. Gravitational lensing works similarly, except space itself is the window, warped by the presence of enormous mass. The stronger the gravitational field, the more dramatic the distortion. The Great Attractor region produces lensing effects visible to modern telescopes, confirming its extraordinary mass concentration. But mass alone doesn't tell the whole story. The Great Attractor isn't static. It's dynamic, constantly evolving as galaxies fall into it, merge with existing members, and add their mass to the growing concentration. Billions of years ago, this region looked different, less massive, less centralized. Billions of years in the future, it will look different still, as more galaxies arrive and settle into the gravitational well. The universe expands, driven by dark energy, but within regions like the Great Attractor, gravity wins. Galaxies here aren't participating in cosmic expansion. They're falling together, fighting against the universe's tendency to spread everything apart. This is confirmed. Local gravitational binding overcomes expansion within sufficiently dense regions. The Great Attractor is one of those regions, a place where gravity has triumphed over expansion, at least temporarily. Yet even this massive gravity, even this concentration of tens of thousands of galaxies, even this structure that dominates our cosmic neighborhood, turns out to be just one piece of something incomprehensibly larger. For most of human history, Earth was the center of everything. Then we learned Earth orbits the bright star in our sky. Then we learned that star is one of billions in a galaxy. Then we learned our galaxy is one of billions in the observable universe. Each discovery pushed us farther from the center, made our home seem smaller and less significant. In 2014, astronomers added another line to our cosmic address, one that puts us in a structure so vast it challenges the mind's ability to comprehend scale. They named it Laniakea. In Hawaiian, this means immeasurable heaven. The name fits. Laniakea is a supercluster of galaxies, a gravitational basin containing approximately 100,000 large galaxies and an uncountable number of smaller ones. It spans 500 million light-years from edge to edge. Light takes 500 million years to cross it. When light now reaching us from Laniakea's far edge began its journey, the first land animals were crawling out of Earth's oceans. The discovery of Laniakea came from the same cosmic flow mapping that revealed the Great Attractor. By charting the velocities of thousands of galaxies, astronomers could trace the streamlines, showing how matter moves through space. These streamlines revealed boundaries, edges where flow in one direction stops and flow in another direction begins. Like watersheds on Earth, where water on one side of a ridge flows to one ocean and water on the other side flows to a different ocean. Cosmic watersheds divide galaxies flowing toward different gravitational basins. Laniakea is one such basin. Every galaxy within its boundaries is flowing toward the Great Attractor region at its center. The Milky Way is part of Laniakea. So is Andromeda. So is the entire local group, the Virgo cluster, the Hydra Centaurus supercluster, and hundreds of thousands of other galaxies spread across 500 million light-years of space. All of us, all of these structures, share a common destiny, falling together toward the gravitational heart of our supercluster. Think of Laniakea as a cosmic valley. Galaxies are like raindrops falling on the surrounding mountains, running downhill, merging into streams, combining into rivers, all flowing toward the lowest point. The Great Attractor sits at that lowest point. It's not a physical place in the traditional sense, but rather the gravitational center toward which everything else falls. This is confirmed through extensive velocity mapping and is considered one of the landmark discoveries in understanding large-scale structure. The mass of Laniakea is staggering. 100,000 large galaxies, each containing hundreds of billions of stars, plus all the dark matter binding them together, adds up to approximately 100 quadrillion times the mass of our star. Written out, that's 100,000 trillion stellar masses. The number is so large it loses meaning. It's like trying to understand the difference between $1 billion and $1 trillion. Your brain knows one is bigger, but can't truly grasp the scale. Yet Laniakea isn't gravitationally bound. This is a crucial distinction confirmed by cosmological simulations. A gravitationally bound structure holds together despite the expansion of the universe. Galaxy clusters are bound. The local group is bound. But Laniakea is so large, and the expansion of space so strong at these scales that it will eventually disperse. The galaxies at the edges are already being pulled away by the expansion. Only the central region, around the Great Attractor, will remain bound over cosmic time. Our cosmic address now reads Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Cluster, Virgo Supercluster, Laniakea Supercluster. 7 levels of organization, each vastly larger than the one below it. 7 nested structures, each subject to the gravitational influence of all the others. We're not just orbiting one star, we're falling through a hierarchy of cosmic structures, each pulling us in different directions, each contributing to our motion through space. The discovery of Laniakea showed that the Great Attractor wasn't an isolated phenomenon. It was the defining feature of our supercluster, the gravitational anchor organizing motion across 500 million light-years. But defining Laniakia's boundaries raised a troubling question. Where do its boundaries end and other structures begin? Imagine trying to map an ocean while floating in the middle of it. You can see the water around you, measure currents, track waves, but understanding the ocean's full extent, seeing where it borders continents, knowing its deepest points and shallowest shallows, requires a perspective you don't have. Mapping Laniakea presented astronomers with exactly this problem. We sit inside the structure we're trying to measure, embedded in a flow of galaxies we're trying to chart from the inside. The breakthrough came from precisely measuring the distances and velocities of thousands of galaxies. Previous maps relied on redshift alone, which combines cosmic expansion and peculiar velocity into one number. The new approach separated these components. By knowing both how fast a galaxy is moving away due to expansion and how fast it's moving due to local gravity, astronomers could trace the gravitational field itself. Think of it like mapping wind patterns on Earth. You don't just measure how fast the air is moving. You measure which direction it's moving and what's causing that motion. The resulting map showed something breathtaking. Laniakea isn't a blob or sphere of galaxies scattered randomly through space. It's a web, a network of filaments and sheets, connected and organized by gravity. The major concentrations of galaxies form nodes where multiple filaments intersect. The Great Attractor region is the largest node, but others exist throughout the structure. Between the filaments lie voids, vast regions containing few galaxies, where gravity pulls outward instead of inward. The Virgo cluster, containing over 1,000 galaxies and sitting 60 million light-years from us, forms one of Laniakea's major nodes. The Hydra Centaurus supercluster, farther out, forms another. The Norma cluster at the Great Attractor forms the central node. These structures aren't separate. They're connected by bridges of galaxies, cosmic highways along which matter flows. The entire supercluster looks like a three-dimensional spiderweb, with dense junctions connected by thinner strands. Galaxies along the filaments move faster than galaxies in the voids. This makes sense. The filaments contain more mass, generating stronger gravitational pull. Think of rivers flowing downhill. Water in the main channel moves fastest. Water inside pools and eddies moves slower, or not at all. Laniakea's filaments are the main channels, pulling galaxies toward the Great Attractor at high speeds. The voids are the still pools, where galaxies drift slowly or even move away from the supercluster entirely, pulled by gravitational influences beyond its boundaries. The supercluster contains an estimated 500 galaxy groups and clusters. Some are small, containing just a dozen large galaxies. Others are massive, containing thousands. The Virgo cluster alone has more than 1,000 galaxies mapped so far, probably many more too faint to detect. The Fornax cluster, another major structure within Laniakea, contains hundreds of massive galaxies. Each cluster contributes to the overall gravitational field. Each pulls on its neighbors. Each participates in the cosmic dance that defines our supercluster's evolution. Dark matter dominates the mass distribution. For every kilogram of normal matter in Laniakea, roughly 6 kilograms of dark matter lurk invisibly in the same space. This dark matter forms the gravitational scaffolding on which normal matter accumulates. Without it, galaxies wouldn't form clusters. Clusters wouldn't form superclusters. The large-scale structure of the universe would look completely different. Dark matter's presence is confirmed through multiple lines of evidence, from galaxy rotation speeds to gravitational lensing to the cosmic microwave background radiation. The flow of galaxies within Laniakea isn't uniform. Some regions show fast motion, others slow. Some galaxies rush directly toward the Great Attractor. Others take roundabout paths, spiraling inward while also moving sideways. These variations reveal the complexity of the gravitational field, the way multiple mass concentrations compete and cooperate to shape motion on the largest scales. Here's what keeps astronomers awake at night. Laniakea is enormous. It contains 100,000 galaxies spread across 500 million light-years. It's one of the largest structures we've discovered. Yet galaxies at its edges show motion that can't be explained by Laniakea's mass alone. They're being pulled by something beyond, something bigger, something that makes even this immeasurable heaven look small by comparison. The streamlines mapping Laniakea look like rivers on a three-dimensional terrain map. Start at any galaxy in the supercluster, trace its motion backward through time, and you'll follow a path that winds through space, passing near other galaxies, curving around dense regions, eventually leading to the Great Attractor. Now repeat this for 100,000 galaxies. The resulting network of paths creates a visualization so beautiful and so strange it looks like art rather than science. But these aren't artistic interpretations. These are real trajectories based on measured velocities. Every line represents the actual path a galaxy takes as it falls through Laniakea's gravitational field. Where lines converge, matter accumulates. Where lines spread apart, voids form. The pattern reveals not just where galaxies are now, but where they came from and where they're going. Some streamlines extend beyond Laniakea's boundaries. These represent galaxies on the edge, uncertain whether they'll remain part of the supercluster or get pulled away by competing gravitational influences. Think of a river delta where the main channel splits into multiple branches before reaching the ocean. Some water flows one way, some another, and the dividing line shifts constantly as conditions change. Laniakea's boundaries work similarly, with galaxies near the edge experiencing a gravitational tug-of-war between our supercluster and neighboring structures. The Milky Way's trajectory can be traced with high precision. We're moving at 600,000 miles per hour toward the Great Attractor, but we're also moving sideways relative to other structures. Our path is a long, slow spiral, circling inward while also being pulled deeper into the gravitational well. In 10 billion years, assuming no other factors change, we might reach the densest part of the Great Attractor region, but other factors will change. The universe's expansion, driven by dark energy, will eventually overcome even these massive gravitational pulls. Other galaxies follow similar paths. Andromeda, our nearest large neighbor, flows toward the Great Attractor along a streamline nearly parallel to ours. In about 4 billion years, Andromeda will collide with the Milky Way. The two galaxies will merge into one larger galaxy, probably an elliptical rather than a spiral. But even this merged galaxy will continue falling toward the Great Attractor, following the streamline that both galaxies were already traveling. The Virgo cluster's streamline shows it plunging toward the Great Attractor region at over 1 million miles per hour. Dozens of other clusters follow their own streamlines, each converging on the central basin. Over billions of years, these clusters will continue falling inward. Some will merge with existing structures in the Great Attractor region. Others will pass through and emerge on the far side, only to fall back in again later, like a pendulum swinging back and forth. This infall isn't gentle. When galaxies fall into dense regions, they experience tidal forces that can tear them apart. Stars get stripped away, forming long streams of stellar debris. Gas gets compressed, triggering bursts of new star formation. The act of falling changes galaxies fundamentally. The galaxies we see in the Great Attractor region today look different from galaxies in less dense parts of Laniakea. They're redder, older, containing fewer young stars. This is because their gas was stripped away during infell, shutting down star formation. The streamlines also reveal the history of Laniakea. By running the flow backward in time, astronomers can see where galaxies were billions of years ago. The supercluster was less concentrated then, more spread out. Galaxies near the edges hadn't yet felt the full pull of the Great Attractor. The structure was younger, less organized, still in the process of coalescing from the initial density fluctuations that formed after the Big Bang. Looking forward in time tells a different story. The streamlines suggest that in the distant future, assuming dark energy doesn't tear everything apart first, much of Laniakea will collapse into a single massive structure. The individual galaxy clusters will merge, the filaments will condense, everything flowing toward the Great Attractor will eventually arrive. The result would be one of the largest galaxy clusters in the universe, containing the combined mass of hundreds of thousands of galaxies. But that future won't happen. Dark energy, the mysterious force driving cosmic expansion, grows stronger as the universe ages. Eventually, it will overcome gravity even at these scales. The expansion will accelerate, pulling Laniakea apart. The streamlines we map today show motion toward the center. In the far future, those streamlines will reverse, showing motion away from the center as expansion dominates. For now, though, the rivers flow inward. 100,000 galaxies, all falling together, all following paths determined by gravity and the initial conditions set 13.8 billion years ago at the beginning of time. And beyond Laniakea's boundaries, even mightier currents are pulling. 1,300,000 miles per hour. That's how fast the Milky Way is moving toward the Great Attractor. To put that in perspective, a spacecraft traveling that fast could reach the Moon in 11 minutes. It could reach Mars at its closest approach in 3 hours. It could reach Neptune at the edge of our solar system in about 4 days. We're hauling through space at speeds that would be considered impossible for any spacecraft humans have ever built. But here's the strange part. You don't feel it. Earth's motion around the star's motion around the galaxy's motion through space. None of it produces forces you can sense. Everything moves together. You, Earth, the entire solar system. We're all passengers on this cosmic journey, all traveling at the same velocity. There's no reference point to measure against, no stationary wall to watch sliding past. Motion only becomes apparent when you look at other galaxies and measure how their light shifts. The speed varies depending on which structure you're measuring relative to. Compared to the cosmic microwave background, the radiation left over from the Big Bang, the Milky Way moves at about 800,000 miles per hour. Compared to the local group's center of mass, we're moving at roughly 300,000 miles per hour. Compared to the Great Attractor, we're traveling at 1,300,000 miles per hour. Each measurement is correct. Each describes motion relative to a different reference frame. Think of sitting in a car on the highway. Relative to the car, you're stationary. Relative to the road, you're moving at 60 miles per hour. Relative to someone in another car going 70 miles per hour, you're moving backward at 10 miles per hour. All three measurements are true simultaneously. The same principle applies on cosmic scales, except instead of miles per hour, we measure millions of miles per hour, and instead of cars on a highway, we measure galaxies falling through curved space. Andromeda moves toward us at about 70 miles per second, or 250,000 miles per hour. This is separate from the cosmic flow. Andromeda and the Milky Way are gravitationally bound to each other, falling together in a slow collision that will take billions of years to complete. Meanwhile, both galaxies, along with all the other members of the local group, are falling toward the Great Attractor together. We have motion within motion within motion, each component adding to create our total velocity through space. The Virgo cluster races toward the Great Attractor even faster than we do. Its distance puts it deeper in the gravitational well, where the pull is stronger. Galaxies on the near side of Virgo, the side facing us, move at slightly different speeds than galaxies on the far side. This velocity gradient across the cluster reveals the strength and direction of the gravitational field. It's like watching a stream of water accelerate as it flows downhill. Galaxies closer to the source of gravity move faster than galaxies farther away. These speeds are confirmed through multiple independent measurements. Astronomers measure redshift, the stretching of light from receding objects. They measure blue shift, the compression of light from approaching objects. They use multiple techniques to determine distances, which combined with velocities reveal the three-dimensional motion of galaxies through space. The data all agrees. The Milky Way is falling toward the Great Attractor at over 1 million miles per hour, and nothing can stop this motion. Well, almost nothing. Dark energy can stop it. In fact, dark energy will stop it. The expansion of the universe, driven by this mysterious force, grows stronger with time. Eventually, expansion will overcome the gravitational pull of the Great Attractor. Laniakea will begin dispersing. Galaxies at the edges will be pulled away first, then galaxies closer to the center. Finally, even the core structures will feel the effects. But that's billions of years in the future. For now, gravity dominates. For now, we fall. The speed also reveals something about the mass pulling us. Newton's law of gravity states that the force depends on mass and distance. By measuring how fast galaxies move at different distances from the Great Attractor, astronomers can calculate the mass distribution, creating that pull. The faster the motion, the more mass must be present. The calculations confirm tens of thousands of galaxies worth of mass concentrated in the Great Attractor region, mostly in the form of dark matter we cannot directly see. But here's where the numbers stop making sense. The velocities of galaxies far from the Great Attractor suggest they're being pulled by something even more massive lying beyond. Our cosmic journey isn't just toward the Great Attractor, it's toward something larger, something that makes our already incredible speed seem like just the beginning. By the early 2000s, astronomers believed they had solved the Great Attractor mystery. They had mapped the Norma cluster. They had discovered Laniakea. They had traced the cosmic flows showing how galaxies moved through space. The picture seemed complete. The Great Attractor was the gravitational center of our supercluster, pulling everything toward it through the combined mass of multiple galaxy clusters hidden behind the zone of avoidance. Case closed. Except the observations kept showing anomalies. Galaxies on the far side of Laniakea, the side away from the Great Attractor, moved faster than they should. Their velocities suggested something beyond Laniakea was pulling on them. Not a small pull. A massive pull, stronger than what the Great Attractor generated. Scientists checked their measurements. They recalculated distances. They verified velocities using multiple independent methods. The anomaly remained. Then came the surveys that changed everything. The Cosmic Flows project continued expanding, adding more galaxies to their maps, pushing the boundaries of known structure deeper into space. By 2005, they had mapped galaxy motions out to 650 million light-years, far beyond Laniakia's boundaries. The data revealed something that shouldn't exist according to standard cosmological models. The Great Attractor itself was moving, not just participating in cosmic expansion, moving with peculiar velocity towards something else, something farther out, something more massive. Think about that. The structure pulling on 100,000 galaxies, the gravitational center of Laniakea, the mass concentration equivalent to tens of thousands of galaxies, was being pulled by something even larger. It was like discovering that the ocean you thought was the biggest body of water is actually just a bay, connected to a larger ocean beyond the horizon. This larger structure had a name. The Shapley supercluster, discovered by Harlow Shapley in the 1930s, was the most massive concentration of galaxies in the observable universe nearby. It sits 650 million light-years away, beyond Laniakea, beyond the Great Attractor, in a region where observations become difficult, but not impossible. Shapley contains tens of thousands of galaxies, far more than the Great Attractor region. Its mass creates a gravitational pull that extends across nearly 1 billion light-years of space. The X-ray surveys conducted in 2005 measured the Great Attractor's mass with high precision. The result shocked researchers. The Great Attractor contained only about 1/10 the mass that previous estimates suggested. Instead of 100,000 galaxies, it contained about 10,000. Still enormous, still the dominant structure in Laniakea, but not nearly as massive as needed to explain all the observed motions. This created a crisis in cosmology. If the Great Attractor wasn't massive enough to pull galaxies at the speeds observed, what was? The answer lay beyond, in the Shapley region. But accepting this answer meant accepting that our understanding of large-scale structure was incomplete. It meant accepting that Laniakea wasn't a self-contained supercluster, but rather part of an even larger system. It meant redrawing maps and rethinking theories about how gravity organizes matter on the largest scales. Some astronomers resisted this conclusion. They argued the measurements were wrong, or the interpretation flawed. They suggested dark matter distribution might explain the discrepancy without needing a larger attractor beyond Laniakea. They proposed alternative theories involving cosmic voids pushing from behind, rather than attractors pulling from ahead. Each theory had problems. Each failed to explain all the observations. The evidence kept accumulating. More surveys, more data, more galaxies added to the maps. Every new measurement pointed toward the same conclusion. The Milky Way, along with Laniakea, along with the Great Attractor, along with everything in our cosmic neighborhood, was falling toward the Shapley supercluster. This was confirmed in multiple independent studies using different methodologies. The scientific consensus shifted. What seemed like the answer turned out to be just another step in a longer journey. The Great Attractor was real. Its gravitational influence was real. But it was part of something bigger, a stepping stone on a path toward an even more massive destination. Astronomers had been looking at one tree and missing the forest. The forest stretched farther than anyone had imagined, and somewhere in its depths, something colossal was pulling on everything within reach. The Shapley supercluster doesn't hide behind a zone of avoidance. It sits in clear sky, observable with optical telescopes, visible to anyone who knows where to point their instrument. Scientists discovered it nearly a century ago. So why did it take so long to realize it was pulling on our galaxy? Because its distance made it seem irrelevant to local dynamics. 650 million light-years is so far that most astronomers assumed its gravitational influence would be negligible at our location. They were wrong. Gravity falls off with distance, but it never completely disappears. The farther you get from a massive object, the weaker its pull, but the math shows gravity extending infinitely outward. For practical purposes, beyond a certain distance, gravitational effects become too small to measure. Shapley sits right at the edge of that practical limit. Its pull on the Milky Way is weak compared to local sources, but it's measurable. And when you account for Shapley's mass, that weak pull adds up to significant motion over cosmic time. The numbers are staggering. The Shapley supercluster contains approximately 100,000 galaxies in its core, similar to Laniakea. But its overall mass distribution extends much farther. When astronomers map the full extent of Shapley's gravitational influence, they find it affects structures across more than 1 billion light-years of space. This makes it one of the largest gravitational domains in the nearby universe. Think of gravitational influence like a sphere expanding outward from a mass concentration. The bigger the mass, the bigger the sphere. Shapley's sphere is so large it encompasses Laniakea. We sit inside Shapley's gravitational domain, even though we're nowhere near its core. We're falling toward it, just very slowly compared to structures closer to its center. Over billions of years, this slow fall accumulates into significant motion. Measurements of galaxy velocities toward Shapley show exactly this pattern. Galaxies closer to Shapley move faster toward it. Galaxies farther away move slower but still show directional bias. The Milky Way's motion, when all factors are considered, includes a component pointing toward Shapley. The Great Attractor also moves toward Shapley. Laniakea as a whole is falling toward this even more massive structure. This revelation forced astronomers to reconsider the definition of a supercluster. Is Laniakea a separate structure, or is it part of Shapley? Where do you draw the boundary? The question has no easy answer. Some scientists argue that basins of attraction define superclusters, in which case Laniakea is separate because galaxies within it flow toward the Great Attractor rather than directly toward Shapley. Others argue that gravitational influence defines superclusters, in which case Laniakea is part of Shapley because Shapley's gravity affects everything within Laniakea. Recent surveys suggest Laniakea might be just one sub-basin within a larger Shapley basin of attraction. Imagine a valley with multiple streams feeding into it. Each stream has its own small valley where water collects before flowing into the main valley. Laniakea would be one of these small valleys, the Great Attractor its lowest point. But the main valley is Shapley, the ultimate destination where all the small valleys eventually drain. The discovery of Shapley's dominance came from analyzing cosmic flows with unprecedented precision. By mapping tens of thousands of galaxies and calculating their three-dimensional velocities, astronomers could trace motion on the largest scales. The patterns showed unambiguously that structures in our region of the universe are falling towards Shapley. Not just falling, but accelerating as they get closer, pulled by gravity that grows stronger with proximity. This creates a hierarchy of motion. The Milky Way orbits within the local group. The local group falls toward the Virgo cluster. The Virgo cluster falls toward the Great Attractor. The Great Attractor falls toward Shapley. Each level of organization moves in response to gravitational pull from the next level up. It's like nested Russian dolls, except each doll is moving relative to the one containing it. But even Shapley's influence has limits. Galaxies beyond a certain distance don't participate in the flow toward it. They're caught in other basins of attraction, pulled by other massive structures in other parts of the universe. The cosmic web consists of multiple superclusters, each creating its own gravitational domain, each pulling on galaxies within reach. Shapley is just one node in this vast network, albeit one of the most massive nodes in our neighborhood. Here's what keeps cosmologists awake at night. If something as massive as Shapley can influence structures a billion light-years away, what else might be out there, beyond our current survey limits, pulling on things we can observe? The universe is 13.8 billion light-years in radius for light reaching us. We've only mapped galaxy motions out to about 1 billion light-years. What happens at 2 billion? At 5 billion? At 10 billion? The hierarchies might continue, structures nested within structures, pulling within pulling, across scales we haven't yet discovered. When astronomers calculated the volume of Shapley's basin of attraction, the numbers defied their expectations. Laniakea spans 500 million light-years and contains about 100,000 galaxies. Shapley's basin, according to the latest measurements, spans 10 times that volume. Not 10 times the diameter, 10 times the volume. This is a confirmed finding from multiple studies analyzing cosmic flows across billions of light-years. Volume grows with the cube of radius. If you double the radius of a sphere, you multiply its volume by 8. If you triple the radius, you multiply the volume by 27. Shapley's basin has roughly twice the radius of Laniakea, which means its volume is approximately 8 to 10 times larger. The mass contained within this basin is correspondingly enormous, though exact numbers remain uncertain due to the difficulty of measuring dark matter at these distances. This basin might contain 1 million galaxies, maybe more. The surveys haven't catalogued them all yet. Many lie too far away for precise distance measurements. Others hide in regions where dust or bright foreground objects obstruct the view. Estimates suggest hundreds of thousands of large galaxies and millions of smaller dwarf galaxies populate Shapley's basin. Each contributes to the overall gravitational field. Each participates in the cosmic flow toward the basin's center. The Shapley core itself is a monster. Multiple massive galaxy clusters, each containing thousands of galaxies, crowd into a relatively small region of space. These clusters are so close together, they interact gravitationally, pulling on each other, distorting each other's shapes. Some are in the process of merging, colliding at speeds of millions of miles per hour. The resulting collisions generate enormous amounts of energy, heating gas to temperatures exceeding 100 million degrees Fahrenheit. Think of Shapley's core as a cosmic traffic jam. Imagine hundreds of galaxy clusters, each the size of a substantial supercluster, all trying to occupy the same region of space. They don't have physical surfaces to collide with, so they pass through each other, but their gravitational fields interact violently. Stars from different clusters mix together. Gas clouds collide and shock heat. Dark matter halos overlap and disturb each other's orbits. The result is chaos on the largest imaginable scale. X-ray observations of Shapley show it glowing brilliantly in high-energy radiation. This glow comes from the hot gas between galaxies, gas heated by the energy of countless collisions and gravitational interactions. The temperature is so high that atoms cannot hold onto their electrons. The gas exists as plasma, a fourth state of matter where nuclei and electrons move independently. This plasma fills the space between clusters, connects them into a web, and contains more mass than all the visible stars in all the galaxies combined. Shapley's basin extends far beyond the core clusters. Filaments of galaxies stretch outward, connecting the core to more distant structures. These filaments trace the dark matter web underlying all visible structure. Where filaments intersect, galaxy clusters form. Where they stretch between nodes, galaxies string out in long chains. The pattern resembles a spider web again, but on a scale that makes Laniakea look like a single thread in a much larger tapestry. The discovery that we exist within Shapley's basin of attraction challenged theoretical predictions about how large structures can grow. According to standard cosmological models, there hasn't been enough time since the Big Bang for gravity to organize matter on such enormous scales. Structures like Shapley should still be in the early stages of formation, not already massive and dominant. Yet here it is, confirmed through observations, defying expectations. Some theories suggest Shapley formed earlier than typical structures, perhaps due to unusual initial conditions in that region of space after the Big Bang. Others propose that dark matter properties might differ slightly from standard assumptions, allowing faster structure growth. A few scientists question whether standard cosmology fully explains what we observe, suggesting modifications might be needed to account for structures like Shapley. The debate continues. What's certain is that Shapley exists, that it's massive, and that it's pulling on everything in our cosmic neighborhood, including the Milky Way. We're falling toward it, along with Laniakea, along with the Great Attractor, along with hundreds of thousands of other galaxies caught in the same immense gravitational current. And if Shapley can be 10 times larger than we expected, what else might we discover when we push surveys even farther into space? Galaxies don't just get pulled, they also get pushed. Between the massive structures like Shapley and Laniakea lie voids, enormous regions of space containing very few galaxies. These voids aren't empty vacuum. They contain dark matter, just much less of it than surrounding regions. And this deficit creates something unexpected. Cosmic voids act like repellers, pushing galaxies away from their centers toward denser regions at their edges. Think of it this way. Gravity pulls toward mass. In a region with less mass, like a void, there's less pull inward and more pull outward toward the massive structures surrounding the void. Galaxies near a void's edge feel gravity pulling them away from the empty space and toward the walls where more galaxies cluster. The void doesn't actively push, it simply fails to pull, which in a universe full of pulling forces creates an effective repulsion. The dipole repeller is one such structure. This is a confirmed feature of the cosmic web, a vast void sitting in the opposite direction from Shapley relative to the Milky Way. While Shapley pulls us forward, the dipole repeller pushes from behind. The combined effect accelerates our motion more than either force alone could achieve. We're not just falling toward Shapley, we're also being pushed away from an underdense region behind us. This creates a tug of war across cosmic distances. Shapley pulls from one direction. The dipole repeller pushes from the opposite direction. The Great Attractor pulls from a third direction. Other structures pull or push from other angles. The Milky Way's actual motion is the sum of all these forces, a complex vector resulting from gravitational influences extending across 1 billion light-years. Galaxies sitting between major structures experience the most dramatic effects. They feel pulls from multiple directions simultaneously. Their motion becomes unpredictable, chaotic even, as they navigate the gravitational landscape. Some end up falling toward one attractor, others fall toward different attractors. A few, sitting exactly between competing influences, barely move at all relative to cosmic expansion, balanced precariously in gravitational equilibrium. The boundaries between basins of attraction mark where one gravitational influence ends and another begins. These boundaries aren't sharp lines. They're fuzzy transition zones where the tug of war is most intense. Galaxies in these zones can switch allegiance, so to speak, pulled first toward one attractor and then toward another as their positions and the mass distributions slowly evolve. Think of watersheds on Earth. Rain falling on one side of a mountain ridge flows to one river system. Rain falling on the other side flows to a different system. The ridge marks the boundary. But the ridge isn't a knife-edge line. It's a gradual transition where water might flow one way or another depending on subtle features of the terrain. Cosmic watersheds work similarly, except the terrain is curved space-time, and the water is galaxies falling through gravitational fields. The local group sits in a relatively simple part of this landscape. We feel strong pull from the Virgo cluster, which is part of Laniakea, which flows toward the Great Attractor, which falls toward Shapley. The influences stack neatly, all pointing in roughly the same direction. But galaxies in other parts of the cosmic web face more complex situations. They might feel equally strong pulls from two different attractors in perpendicular directions. Their resulting motion becomes a compromise, falling toward neither attractor directly, but instead taking a curved path between them. This tug-of-war has existed since shortly after the Big Bang. When the universe was young, matter was distributed almost uniformly, with only tiny density variations. These variations were the seeds of future structures. Regions that were slightly denser than average had slightly stronger gravity. This pulled more matter toward them, increasing their density further, strengthening their gravity more, creating a feedback loop. Over billions of years, these small variations grew into the massive structures we see today. The tug-of-war will continue into the far future. Attractors will keep pulling. Voids will keep pushing. Galaxies will continue falling through the gravitational landscape. But eventually, dark energy will dominate. The expansion of the universe will accelerate until it overcomes even the strongest gravitational pulls. The basins of attraction will disperse. The cosmic web will tear apart. The tug-of-war will end, not because one side won, but because the rope itself stretched and broke. For now, though, the battle continues. Forces beyond our control pull the Milky Way across the cosmos. We're caught in currents we cannot resist, falling toward destinations we may never reach. Everything you've learned so far about the Great Attractor, about Laniakea, about Shapley, everything about the cosmic web and gravitational flows, all of it rests on something we cannot see: dark matter. This invisible substance makes up 85% of all matter in the universe. It doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation in any detectable way. Yet, its gravitational influence shapes the largest structures in existence. Think of dark matter as the skeleton beneath the skin. You see the skin, the visible galaxies and gas clouds. But the skeleton underneath determines the shape, provides the structure, holds everything together. Without dark matter, galaxies would fly apart, clusters would dissolve, the cosmic web would never have formed. Stars might not even exist because the density fluctuations needed for structure formation wouldn't have grown large enough in the time available since the Big Bang. This is confirmed through multiple lines of evidence. Galaxies rotate too fast to be held together by the gravity of visible matter alone. Stars near galaxy edges move at the same speeds as stars near galaxy centers, which shouldn't happen if visible matter were all that existed. Gravitational lensing, the bending of light around massive objects, shows far more mass than visible matter can account for. The cosmic microwave background radiation, light from the early universe, contains patterns that only make sense if dark matter dominated the mass distribution back then. the Great Attractor region contains vastly more dark matter than normal matter. For every kilogram of stars and gas, there's roughly 6 kilograms of dark matter lurking invisibly in the same space. This dark matter forms the gravitational well into which galaxies fall. The visible structures we observe are just the bright foam on top of a much deeper ocean of invisible mass. Dark matter doesn't cluster exactly the same way normal matter does. Normal matter can collide, radiate energy, cool down, and collapse into dense concentrations like stars and planets. Dark matter doesn't collide, doesn't radiate, doesn't cool. It forms diffuse halos around galaxies and clusters, spread out over enormous volumes. These halos overlap, merge when clusters collide, and create the gravitational scaffolding on which the cosmic web hangs. Simulations of structure formation run on supercomputers show exactly this. Start with a universe filled uniformly with dark matter and normal matter. Let gravity work. Fast forward billions of years. The result looks remarkably like the universe we observe. Filaments form, connecting nodes of high density. Voids form between filaments. Galaxy clusters grow at nodes. The pattern emerges naturally from gravity, acting on dark matter, with normal matter following dark matter's lead. Without these simulations, astronomers couldn't make sense of observations. The motions of galaxies toward the Great Attractor, the structure of Laniakea, the influence of Shapley. None of it fits unless you include dark matter in the calculations. When you add dark matter, everything falls into place. The masses work out. The velocities make sense. The gravitational fields match predictions. Dark matter isn't just a convenient explanation. It's a necessary component of the theory that explains how the universe evolved from a smooth beginning to the complex web we see today. Scientists still don't know what dark matter is made of. The leading theory suggests it's a new type of particle, something that doesn't interact with normal matter except through gravity. Dozens of experiments search for these particles, trying to detect them passing through Earth. So far, none have succeeded definitively. Dark matter remains invisible, its nature unknown, its properties uncertain except for one thing. It has mass, and mass generates gravity. The distribution of dark matter in the Great Attractor region can be mapped using gravitational lensing. Light from distant galaxies passes through the region, gets bent by dark matter's gravity, and arrives at our telescopes distorted. By measuring these distortions, astronomers can reconstruct where dark matter concentrates and where it's sparse. The maps show dark matter forming a web-like pattern with dense nodes connected by thinner filaments, exactly as simulations predict. This invisible scaffolding extends across the entire observable universe. Every structure, from small dwarf galaxies to superclusters like Shapley, sits embedded in dark matter halos. The visible universe is just the tip of the iceberg. The bulk of the mass, the bulk of the gravitational influence comes from substance we cannot directly detect. We know it exists only by its effects on things we can see. And here's what should disturb you. We're being pulled across the cosmos by something we cannot observe, made of something we don't understand, toward a destination determined by forces operating on scales beyond human comprehension. The Great Attractor is real. The pull is real. But the thing doing the pulling is mostly invisible, mostly unknown, mostly beyond our ability to study directly. We're passengers on a cosmic journey, guided by invisible hands toward an uncertain future. The largest structures in the universe aren't spheres or clusters. They're walls. Imagine a sheet of galaxies stretching across 500 million light-years, thin but impossibly wide, forming a barrier between voids. The Great Wall, discovered in the 1980s, was the first of these structures identified. It spans more than 500 million light-years, contains tens of thousands of galaxies, and forms one of the boundaries of our cosmic neighborhood. But the Great Wall is small compared to what came later. In 2003, astronomers mapping distant galaxies discovered something that shouldn't exist according to standard cosmological models. The Sloan Great Wall, a filament of galaxies stretching 1.4 billion light-years across space. This is confirmed through extensive surveys. Light takes 1.4 billion years to travel from one end to the other. When light left one end of this structure, Earth's oceans were just forming. By the time that light reaches the other end, complex life might have evolved on distant worlds. The Sloan Great Wall isn't just one continuous chain of galaxies. It's a connected series of superclusters, filaments, and smaller walls, all linked by threads of dark matter. The structure forms because matter accumulates along the boundaries between cosmic voids. Think of soap bubbles pressed together. The soap film concentrates where bubbles meet, forming a network of connected surfaces. The cosmic web works similarly, with galaxies concentrating along the surfaces between voids. These walls aren't barriers in any physical sense. Galaxies can pass through them. Light travels through them unimpeded. They're simply regions where the density of galaxies is higher than surrounding space. But their existence reveals something profound about how the universe organized itself after the Big Bang. The initial tiny density variations grew over billions of years, creating a foam-like pattern of matter distribution. Dense regions got denser, sparse regions got emptier. The result is the web we observe today. The Norma Wall, part of the Great Attractor region, forms one of these structures closer to home. It spans over 100 million light-years and contains multiple galaxy clusters, including the Norma cluster at its heart. This wall connects the Great Attractor to surrounding structures, forming part of the filament network that defines Laniakea's shape. Galaxies along the wall move at high speeds, falling toward the densest nodes where gravity is strongest. Walls mark the edges of basins of attraction. Where Laniakea ends and other structures begin, you find walls separating different gravitational domains. These boundaries aren't empty spaces. They're concentrations of galaxies caught between competing pulls, orbiting in the gravitational landscape created by multiple attractors. Some galaxies in these walls will eventually fall into Laniakea. Others will fall into neighboring basins. The walls themselves slowly evolve as galaxies make their choices. The South Pole Wall, discovered in 2020, wraps around Laniakea like a cosmic arm. This structure was hidden from view because parts of it lie behind the zone of avoidance, and other parts sit in the southern sky where fewer telescopes observe. When astronomers finally mapped it using advanced distance measurement techniques, they found a wall comparable in size to the Sloan Great Wall, one of the largest structures known, sitting right in our cosmic backyard. Think about what this means. The largest structures in the universe, walls spanning billions of light-years, exist as boundaries between other structures. They're not rare, they're not unusual, they're fundamental features of how matter organizes on the largest scales. And we're surrounded by them, living inside a cosmic foam where dense walls enclose empty voids. These walls formed from tiny quantum fluctuations in the first fraction of a second after the Big Bang. Those microscopic variations in density, smaller than an atom, expanded with the universe. Over billions of years, gravity amplified them into structures spanning billions of light-years. The walls we see today are the descendants of those primordial ripples, stretched and grown to cosmic scales. But here's what troubles cosmologists. The the walls are too large. There hasn't been enough time since the Big Bang for gravity to organize matter into structures this enormous. Light can only travel so far in 13.8 billion years. Gravitational influences can only propagate at the speed of light. Structures bigger than that distance shouldn't exist, yet they do. Multiple walls exceeding the theoretical size limit have been discovered. Either the models are wrong, or something about the early universe's expansion was different than currently understood. The universe is mostly empty. This isn't poetic exaggeration, it's measured fact. If you selected a random point in space, the overwhelming odds are you would land in a void, a region containing almost no galaxies. These voids span hundreds of millions of light years. Some are larger than Laniakea. They contain maybe a dozen galaxies, where equally sized regions on void walls contain thousands. And these empty spaces shape cosmic evolution just as much as the dense structures do. Voids don't stay empty by accident. They started slightly less dense than average in the early universe. As surrounding regions collapsed under their own gravity, pulling matter inward, the underdense regions lost matter, becoming emptier. It's a runaway process. The more matter leaves a void, the less gravity it has to stop more matter from leaving. Over billions of years, voids grew larger and emptier while surrounding walls grew denser. But voids do more than just empty out. They push, not with any force you can measure directly, but through the absence of gravitational pull. Imagine standing on a hill. Gravity pulls you downward. Now imagine standing at the bottom of a valley between two mountains. Both mountains pull you, but the pulls partially cancel because they come from different directions. The valley doesn't push you up. The mountains just pull you towards their slopes. Voids work the same way, except in 3 dimensions across cosmic distances. The dipole repeller, sitting in the direction opposite from Shapley relative to the Milky Way, is one of the largest known void structures. It spans approximately 300 million light-years and contains far fewer galaxies than expected for that volume of space. The deficit of mass creates an effective repulsion. Galaxies near its edges feel more pull from dense structures on the far side than from the empty void nearby. This asymmetry in gravitational forces pushes galaxies away from the void center. This is confirmed through detailed mapping of galaxy velocities. Galaxies near the dipole repeller move away from it faster than cosmic expansion alone would predict. They're not just expanding away, they're actively being pushed by the gravitational imbalance created by the void's emptiness. The effect adds to the pull from Shapley, accelerating the Milky Way's motion more than either force alone could achieve. Think of it like rowing a boat on a river. The current pulls you downstream toward the ocean. But there's also a wind at your back pushing you in the same direction. You move faster than the current alone would carry you. The Milky Way is that boat. Shapley is the ocean. The dipole repeller is the wind. Both forces combine to accelerate our cosmic journey. The Botha's void, discovered in the 1980s, is one of the largest known voids in the universe. It spans about 330 million light-years and contains only about 60 galaxies, where a typical region of that size contains over 2,000. This void is so empty, so underdense, that its existence puzzled astronomers for decades. How could such a large region become so devoid of galaxies? What happened to all the matter that should be there? The answer involves complex physics about how voids form and grow. Small underdensities in the early universe expanded faster than average regions. As they expanded, matter flowed out toward denser surroundings. This outflow lowered the density further, allowing even faster expansion. The process fed on itself until vast regions were nearly empty, with matter concentrated in the walls surrounding them. Galaxies unlucky enough to form inside voids face lonely existences. They're isolated from the cosmic flows that shape galaxy evolution. They don't merge with other galaxies as often. They don't experience the gravitational interactions that trigger star formation. Many void galaxies are smaller, bluer, and younger looking than galaxies in dense regions. They evolved differently because their environments were different. The boundaries between voids and walls are where the action happens. Galaxies in these transition zones experience the strongest pushes and pulls. They're caught in gravitational rapids, accelerating toward the walls while being pushed from the voids. These galaxies show the highest peculiar velocities, moving at millions of miles per hour relative to cosmic expansion. The Milky Way sits in such a transition zone, not deep in a void, but not deep in a wall either, accelerating under the combined influences of multiple structures. Voids will grow larger as the universe expands. Dark energy drives cosmic expansion, and this expansion is fastest in regions that are already underdense. Voids expand faster than dense regions. Over billions of years, the foam-like structure of the universe will become more exaggerated. Voids will get emptier and larger. Walls will get thinner but denser. Eventually, galaxies will be isolated on tiny, dense nodes separated by enormous empty spaces. But for now, voids and walls exist in a dynamic balance. Voids push galaxies toward walls. Walls concentrate galaxies into attractors. The cosmic dance continues, driven by gravity's relentless pull and the strange effective push of empty space. In 2020, during a global pandemic when humans retreated indoors and observatories shut down, astronomers made a discovery by analyzing old data. They found a massive structure that had been hiding in plain sight for decades. The South Pole Wall, a concentration of galaxies wrapping around Laniakea like a cosmic arm, comparable in size to the largest structures ever discovered, sitting close enough to significantly influence our local gravitational environment. The structure earned its name because the densest part lies in the direction of Earth's south celestial pole. From Earth's surface, this region appears low on the southern horizon. Northern Hemisphere observatories can't observe it well. Even southern observatories struggled because the region contains many bright foreground stars that interfere with detecting faint, distant galaxies. Part of the structure also crosses through the zone of avoidance, hidden behind the Milky Way's dust. Discovering the South Pole Wall required a different approach. Instead of photographing galaxies directly, astronomers used redshift surveys to estimate distances. They measured how light from galaxies was stretched by cosmic expansion, calculated approximate distances from those measurements, and built a three-dimensional map of galaxy positions. The map revealed a connected structure, a filament of galaxies extending in a great arc across 200 degrees of sky. That's more than half a circle. The South Pole Wall wraps from the southern sky, curves around the edge of Laniakea, and extends into the northern sky. Its closest point approaches within 300 million light-years of the Milky Way. Its farthest point sits approximately 500 million light-years away. The structure contains thousands of galaxies connected by filaments of dark matter, all part of a coherent gravitational system. Think of the South Pole Wall as a continental divide for cosmic flows. Galaxies on one side of the wall flow toward Laniakea and the Great Attractor. Galaxies on the other side flow in different directions toward other basins of attraction beyond our local neighborhood. The wall marks a boundary in the gravitational landscape, a ridge separating different drainage basins in the cosmic web. The discovery shocked astronomers because something this massive, this close, had remained undetected for so long. We've been observing galaxies for over a century. We've mapped millions of galaxies across the entire sky. How did we miss a structure comparable to the Sloan, Great Wall sitting in our cosmic backyard? The answer reveals how difficult it is to map the universe from inside it, with biases and blind spots limiting our view. The South Pole Wall connects to the Shapley supercluster. Galaxies along the wall move not randomly, but in organized flows, falling toward Shapley just like Laniakea does. This suggests the South Pole Wall might be part of Shapley's basin of attraction, a filament connecting the core to more distant structures. If true, this makes Shapley's basin even larger than previously estimated, extending across more than 1 billion light-years of space. But measurements remain uncertain. Distance estimates for galaxies in the South Pole Wall have substantial error bars. Some galaxies thought to be part of the wall might actually be foreground or background objects appearing aligned by chance. Confirming the wall's exact extent and mass requires more observations, better distance measurements, more complete mapping of the southern sky. The discovery of the South Pole Wall demonstrates how much we still don't know about our cosmic neighborhood. We've been studying the universe for generations. We've built powerful telescopes. We've mapped millions of galaxies. Yet enormous structures remain hidden, waiting to be discovered. The universe keeps surprising us with features we didn't expect in places we've already looked. And here's the troubling part. The South Pole Wall formed from the same initial conditions as everything else in the universe. The quantum fluctuations in the first moments after the Big Bang, amplified by billions of years of gravitational growth, created this structure. But creating something this large in the time available challenges theoretical limits. The wall shouldn't exist according to standard models. Yet it does, confirmed through observations, forcing scientists to reconsider their understanding of structure formation. The South Pole Wall is one more piece in the puzzle of cosmic architecture. It reveals connections between structures we thought were separate. It shows that Laniakea doesn't exist in isolation, but rather as part of a much larger network, and it hints that even larger structures might be waiting to be discovered, hidden in regions we haven't surveyed carefully, or worse, hidden in regions we cannot observe at all. The Milky Way is falling toward the Great Attractor at 1,300,000 miles per hour. At that speed, how long until we arrive? The math seems simple. The Great Attractor sits 250 million light-years away. Divide distance by speed, and you get the time required. Except the calculation isn't that simple. Space itself expands. Dark energy accelerates this expansion. The Great Attractor isn't stationary, and we're not falling in a straight line. Let's start with the basics. 1,300,000 miles per hour equals about 600 kilometers per second. At that speed, covering 250 million light-years would take approximately 400 billion years. But that assumes constant velocity, no change in direction, and a stationary target. None of those assumptions hold true in an expanding universe. The expansion of space adds distance between us and the Great Attractor, even as we fall toward it. Think of walking on a treadmill. If the treadmill moves at the same speed you walk, you stay in the same place. If it moves slower, you make forward progress. If it moves faster, you fall backward despite walking forward. The Great Attractor is far enough away that cosmic expansion adds significant distance over time, partially countering our gravitational infall. Dark energy complicates this further. This mysterious force drives cosmic expansion and grows stronger with time. As the universe ages, expansion accelerates. Eventually, expansion will overcome the gravitational pull of the Great Attractor. We'll stop falling toward it and start being carried away by expansion. The distance between us will begin increasing despite gravity's pull. This transition is predicted to occur within the next several billion years. So the answer to when will we arrive is probably never. We're falling toward the Great Attractor now, but dark energy will reverse our motion before we get there. We're like a ball thrown upward. Gravity pulls it down, but initial momentum carries it higher. Eventually, gravity wins. The ball stops rising and starts falling. We're in the rising phase, still approaching the Great Attractor due to our current motion, but dark energy will eventually stop and reverse our trajectory. But here's where it gets strange. The Great Attractor itself is moving towards Shapley, so even if we somehow did reach the Great Attractor region, we wouldn't stay there. We'd continue falling toward Shapley, riding along with the Great Attractor like passengers on a train. The journey has multiple stages, each leading to another destination beyond. The local group containing the Milky Way and Andromeda is gravitationally bound. This is confirmed. We will merge with Andromeda in about 4 billion years. The resulting combined galaxy will continue falling toward the Virgo cluster. The Virgo cluster is bound. It will continue falling toward the Great Attractor region. These local motions will continue regardless of what dark energy does on larger scales. So, a more accurate answer is this. The local group will merge into a single galaxy. That galaxy will fall toward the Virgo cluster over billions of years and eventually merge with it. The combined structure will fall toward the Great Attractor region. But before reaching there, dark energy will dominate. Cosmic expansion will accelerate beyond any gravitational pull, and all structures beyond the local group will be carried away by the expansion of space itself. Think of it like a river flowing toward the sea. You start high in the mountains, riding the current downstream. The river gets wider and slower as you descend. Eventually, you reach a delta where the river splits into multiple channels before reaching the ocean. Then, you notice the tide is going out. The ocean is receding. You'll never actually reach the open water because the water itself is draining away faster than the current can carry you. Timescales matter here. The Milky Way and Andromeda will merge in roughly 4 billion years. The combined galaxy might reach the Virgo cluster region in another 5 to 10 billion years. The journey toward the Great Attractor might take 20 billion years or more. But dark energy will dominate in approximately 10 to 15 billion years, ending the infall long before we arrive. There's a poetic irony to this. We're being pulled across the cosmos by the Great Attractor. We've spent decades studying it, mapping it, understanding its influence on our motion. We've traced cosmic flows across hundreds of millions of light years to comprehend where we're going. And the answer is, we'll never get there. We're passengers on a journey with no arrival, travelers approaching a destination we'll never reach, pulled by forces that will ultimately be overpowered by the expansion of space itself. The universe doesn't care about our destination, it only cares about the journey. In 1998, astronomers made a discovery that earned them the Nobel Prize and fundamentally changed our understanding of the universe's fate. They were studying distant supernova explosions, using them as standard candles to measure cosmic distances. The data showed something impossible. The universe's expansion wasn't slowing down as gravity should make it. The expansion was accelerating. Something was pushing space apart, working against gravity, growing stronger as the universe aged. They called this force dark energy. Not because they understood what it was, but because they needed a name for something mysterious that operates in darkness beyond our direct observation. Dark energy is the opposite of gravity. Gravity pulls things together. Dark energy pushes them apart, and dark energy is winning. It makes up roughly 70% of all the energy in the universe. Dark matter makes up 25%. Normal matter, everything we can see and touch, makes up only 5%. This changes everything about the Great Attractor's influence. Gravity from massive structures pulls galaxies together over millions and billions of years, but dark energy pushes them apart over even longer timescales. Locally, within galaxy clusters, gravity dominates. The Milky Way will merge with Andromeda. The local group will remain bound. The Virgo cluster will hold together, but on larger scales, dark energy wins. Laniakea will disperse. The Great Attractor's influence will weaken. Shapley's Basin will tear apart. Think of it as a cosmic balancing act. On one side of the scale sits gravity, pulling matter together, building structures, creating galaxies and clusters and superclusters. On the other side sits dark energy, pushing space apart, dispersing structures, fighting against gravity's tendency to make things clump. For the first several billion years of cosmic history, gravity was winning. Structures grew larger and denser. Then, dark energy began dominating. Now structures can only grow up to a certain size before expansion tears them apart. The Great Attractor sits right at the edge of this transition. Structures within it are bound by gravity. The Norma cluster will remain a cluster. Individual galaxy groups will hold together, but the larger scale flows bringing galaxies toward the Great Attractor will reverse. Galaxies currently falling inward will eventually stop, then begin moving outward as expansion accelerates. The cosmic rivers we've been mapping will reverse their flow. This is confirmed through cosmological models that include dark energy. When you run the math forward in time, accounting for both gravity and dark energy, you find that superclusters like Laniakea are temporary structures. They exist now because the universe is in a transition period. Gravity had enough time to build them, but dark energy hasn't yet had enough time to destroy them. Billions of years from now, they'll be gone, dispersed by the relentless expansion. Galaxies beyond the local group will disappear from view, not because they're destroyed, but because space between us and them will expand faster than light can travel. Their light will never reach us. From our perspective, the universe will appear to be shrinking, containing fewer and fewer galaxies until only the local group remains visible. Everything else will have been carried beyond our cosmic horizon by expansion. This makes the current era special. Right now, we can observe the cosmic web in all its glory. We can map superclusters, we can trace cosmic flows, we can see the large-scale structure that gravity built over billions of years. Future civilizations, billions of years from now, won't have this view. They'll see an apparently empty universe, just their own local galaxies surrounded by darkness, with no evidence that larger structures ever existed. Dark energy is also why we'll never reach the Great Attractor. Our infall velocity is high, but not infinite. Expansions adds distance at a rate that increases with distance. Close structures remain reachable because expansion adds distance slowly. Distant structures are unreachable because expansion adds distance faster than we can fall. The Great Attractor sits in the transition zone, close enough that we're currently approaching it, but far enough that expansion will eventually dominate and carry it beyond reach. Scientists still don't understand what dark energy is. The leading theory suggests it's a property of space itself, a sort of energy density inherent to the vacuum. Einstein's equations allow for such a term, called the cosmological constant. Einstein added it to his equations, then removed it, calling it his biggest blunder. Turns out he was right the first time. Space does have an inherent energy that causes expansion. But the cosmological constant creates problems. When physicists calculate what its value should be based on quantum field theory, they get an answer that's wrong by 120 orders of magnitude. That's one followed by 120 zeros. It's the worst prediction in the history of physics. Either quantum field theory is dramatically wrong, or general relativity is wrong, or we're missing something fundamental about how the universe works. This mystery sits at the heart of modern cosmology. Dark energy dominates the universe's evolution. It determines cosmic fate. It controls whether structures like the Great Attractor remain bound or disperse. Yet we have no idea what it is, where it comes from, or why it has the value it does. We are passengers on a cosmic journey shaped by forces we cannot explain. After decades of study, after mapping the zone of avoidance with radio telescopes and infrared instruments, after tracing cosmic flows and measuring peculiar velocities, scientists still don't completely know what's at the center of the Great Attractor. They've found the Norma cluster. They've identified other massive clusters in the region. They've mapped the Norma wall, but the exact configuration of mass, the precise distribution of galaxies and dark matter remains partially mysterious. Here's what is confirmed. The center of the Great Attractor contains multiple massive galaxy clusters within a relatively small region of space. These clusters are gravitationally interacting, pulling on each other, distorting each other's shapes. The largest is the Norma cluster, with thousands of member galaxies. Others include clusters in the Centaurus region, the Pevothisseku cluster, and several others whose names vary in astronomical catalogues because observations remain difficult. Between the clusters lies hot gas, heated to millions of degrees by the energy of gravitational interactions. This gas emits X-rays that space telescopes can detect. The X-ray emission reveals the temperature and density of the gas, which in turn reveals the gravitational potential of the region. More massive concentrations create deeper gravitational wells, which heat gas to higher temperatures. The X-ray observations confirm the Great Attractor region contains enormous mass. But there's something unusual about the mass distribution. It's not symmetrical. The gravitational pull on surrounding galaxies suggests a complex structure with multiple dense nodes rather than one central concentration. Think of it like a mountain range rather than a single peak. Multiple summits exist, each generating its own gravitational field, and the combined effect creates the overall pull we observe. Dark matter dominates the mass. This is confirmed for all large-scale structures. The visible galaxies and hot gas account for only 15% of the total. The remaining 85% is dark matter, distributed in halos around and between the galaxy clusters. These halos overlap, creating a smooth gravitational field that extends far beyond the visible structures. The dark matter is what really generates the Great Attractor's pull. Some astronomers once speculated there might be something exotic at the center, perhaps a supermassive black hole, millions of times larger than the one at our galaxy's center. Perhaps some unknown type of mass concentration involving dark matter physics we don't understand. Perhaps multiple black holes orbiting each other in the space between clusters. These theories proved unnecessary. Normal structures, galaxy clusters, and dark matter halos are sufficient to explain the observations. But here's what's strange. The Norma cluster, the largest structure in the Great Attractor region, contains only about 1/10 the mass originally estimated for the Great Attractor. early calculations suggested you needed 100,000 galaxies worth of mass to generate the observed pull. Later observations showed the Norma region contains only about 10,000 galaxies worth of visible mass. This discrepancy is what led to the discovery of Shapley's influence. The extra pull comes not from the Great Attractor alone, but from Shapley beyond it. So, in some sense, there isn't really a center to the Great Attractor. It's a region, a concentration, a node in the cosmic web where multiple structures intersect. It's the lowest point in Laniakia's gravitational landscape, the place where cosmic rivers converge. But it's not a thing in the traditional sense. It's more like a location, a coordinate in space defined by the surrounding gravitational architecture. Think of a valley between mountains. The valley floor is the lowest point, where water collects. But the valley isn't a thing. It's a feature of the terrain, defined by the mountains surrounding it. The Great Attractor is like that valley floor. The mountains are the surrounding structures, the voids and walls and filaments of the cosmic web. The Great Attractor exists where and how it does because of the larger pattern. This is confirmed through simulations of structure formation. When you start with a universe filled uniformly with dark matter and tiny density fluctuations, then let gravity work for billions of years. You get structures that look like what we observe. Regions that started slightly denser than average collapse inward, forming nodes where cosmic filaments intersect. The Great Attractor is one such node, formed naturally by gravity working on the initial conditions set at the beginning of the universe. Yet some mystery remains. Parts of the Great Attractor region still hide behind the zone of avoidance. Radio and infrared observations have pierced the veil, but not completely. There might be additional clusters we haven't detected yet. There might be unusual structures or configurations we've missed. The exact three-dimensional layout of galaxies and dark matter in the region remains uncertain. And perhaps that's fitting. The Great Attractor, the feature that dominates our cosmic neighborhood's dynamics, the structure pulling us across the universe, retains some mystery, even after decades of study. We know what it does. We know roughly what it is, but we haven't seen it completely, haven't mapped it fully, haven't illuminated all the darkness at its heart. The zone of avoidance covers 20% of the sky. 20% of the entire observable universe is hidden behind the Milky Way's dust and gas. We've found the Great Attractor in that zone. What else might be hiding there? What other massive structures lurk in the regions we cannot observe, generating gravitational pulls we haven't yet detected, shaping cosmic dynamics in ways we don't understand? This question keeps astronomers awake at night. The Great Attractor was discovered by its effect on galaxy motions, not by direct observation. Scientists noticed peculiar velocities and traced them back to their source. The same technique could reveal other hidden attractors if they exist, but you need good velocity measurements for galaxies across large regions of sky. You need accurate distance estimates. You need to separate local gravitational influences from larger scale flows. It's difficult work, and the zone of avoidance makes it harder. Radio surveys have mapped thousands of galaxies behind the zone. These surveys found clusters and superclusters comparable to structures in visible parts of the sky. The density of galaxies behind the zone matches the density elsewhere. There's no indication that this region is special or unusual except for one thing. We can't see it well with optical telescopes, but within the limits of detection, it looks like the rest of the universe. However, detection limits matter. Radio telescopes can find large galaxies with substantial neutral hydrogen gas. They miss smaller galaxies, galaxies with less gas, galaxies too faint to detect. X-ray telescopes can find massive clusters with hot gas. They miss smaller clusters, groups of galaxies, individual galaxies. Infrared telescopes can penetrate dust better than visible light, but they still struggle with the densest regions. Every technique has blind spots. So could there be another great attractor hiding in the zone of avoidance? Possibly. If such a structure existed, it would need to generate peculiar velocities in surrounding galaxies. Astronomers have been mapping these velocities for decades. They've found the Great Attractor's influence. They've found Shapley's influence. They've found the dipole repeller's influence. No other major anomalies have appeared in the data so far. But so far is the key phrase. Surveys are ongoing. Data keeps accumulating. Future discoveries remain possible. The more troubling question is whether attractors exist beyond the zone of avoidance, in regions we can observe clearly, but so distant or so subtly influential that we haven't detected them yet. The universe extends billions of light years in all directions. We've mapped galaxy motions out to about 1 billion light years with reasonable accuracy. Beyond that distance, measurements become uncertain. Redshift from cosmic expansion dominates over peculiar velocity. Separating the two requires extremely precise distance estimates that current techniques cannot always provide. Think of it like mapping ocean currents. Near shore, you can measure currents accurately with buoys and instruments. Farther out, measurements become sparse and uncertain. You might miss major currents simply because you haven't placed instruments in the right locations. The cosmic situation is worse because we can't place instruments wherever we want. We're stuck in one location, observing everything from Earth, trying to deduce three-dimensional structure from two-dimensional sky positions and one-dimensional velocities. There's also the possibility of attractors so distant, their light hasn't reached us yet. The observable universe has a finite size determined by how far light can travel since the Big Bang. Beyond that distance, we cannot see anything because light from those regions hasn't had time to arrive. But gravity's influence isn't limited by light travel time in the same way. If an enormous structure existed just beyond our observable horizon, we might feel its gravitational pull before we see it. This scenario is unlikely based on current models. The cosmological principle states that the universe is roughly the same in all directions on large enough scales. If there were supermassive attractors just beyond our horizon in one direction, there should be similar structures in other directions. The pattern of galaxy motions should show multiple pulls from different parts of the sky. Instead, we see relatively coherent flows toward known structures like Shapley. But the cosmological principle is an assumption, not a proven fact. It holds up well in observations so far. The cosmic microwave background looks the same in all directions except for tiny fluctuations. Galaxy surveys show similar distributions across different parts of the sky. Everything suggests the universe is statistically uniform. Yet we're basing this on observations from one location at one moment in cosmic time. We could be missing something. The possibility of hidden attractors has practical implications. If another massive structure exists, hidden or undetected, it could be influencing the Milky Way's motion in ways we haven't accounted for. Our calculations of where we're going and how fast we're moving assume we've identified all major gravitational influences. If we've missed one, those calculations could be wrong. We might be falling toward a different destination than we think. This is why surveys continue, why astronomers keep mapping galaxies, measuring velocities, calculating distances. Each new observation refines our understanding. Each new discovery adds to the picture. The zone of avoidance is slowly becoming less avoided as new techniques pierce the veil. And perhaps one day, someone will find another great attractor, hidden for decades in plain sight, pulling on us from a direction we never expected. The Great Attractor and structures like it reveal something profound about where the universe came from and where it's going. These massive concentrations of galaxies grew from tiny quantum fluctuations in the first fraction of a second after the Big Bang. Those microscopic variations in density, smaller than an atom, expanded with space. Gravity amplified them over billions of years into structures spanning hundreds of millions of light years. The cosmic web we observe today is the direct descendant of those primordial ripples. This means the universe's large-scale structure was determined at the beginning. The locations of voids, walls, filaments, and attractors were set by initial conditions 13.8 billion years ago. Gravity merely followed the script written in that first moment, building structures according to a pattern laid down before stars or galaxies existed. We're living in a universe whose architecture was predetermined by quantum randomness in the first instant of creation. But the story doesn't end with structure, formation. Dark energy is tearing the web apart. The expansion of space, accelerating over time, will eventually overcome gravity even in the densest regions. Laniakea will disperse. The Great Attractor will cease attracting. Shapley will fragment into isolated pieces. Over tens of billions of years, the cosmic web will unravel, leaving galaxies isolated in an ever-expanding void. Think of the universe's life cycle in 3 phases. First came the era of structure formation, lasting roughly the first 10 billion years, when gravity pulled matter together faster than expansion pushed it apart. We're currently in the second phase, a brief transition period where gravity and dark energy compete on roughly equal terms. Structures exist but are beginning to feel expansion's effects. Superclusters like Laniakea are bound in their cores but dispersing at their edges. The third phase will last essentially forever, with dark energy dominating completely, pushing all structures apart, accelerating expansion until even galaxies eventually tear themselves apart. The Great Attractor teaches us that we live in a special time. Right now, the universe is rich with structure. Galaxies cluster into groups, groups cluster into clusters, clusters connect via filaments into superclusters. Basins of attraction organize motion on the largest scales. We can map this structure, study it, understand how it formed and how it evolves. Future observers, billions of years from now, won't have this opportunity. They'll see a sparse universe containing only their local galaxies, with no evidence that larger structures ever existed. This has philosophical implications. The universe we observe isn't eternal, it's temporary, a snapshot of one phase in cosmic evolution. The structures that seem permanent, like the Great Attractor and Laniakea, are actually transient features that will exist for a finite period before dissolving into the expanding void. Billions of years ago, these structures didn't exist. Billions of years in the future, they won't exist again. We happen to live during the brief window when they're visible. Some cosmologists find this troubling. The anthropic principle suggests we shouldn't be surprised to find ourselves in a time and place where conditions allow observation. If the universe were too young, life couldn't have evolved. If too old, stars would have burned out and galaxies dispersed. We necessarily exist during the window when both life and observable cosmic structure are possible. But that window is closing. Not in our lifetimes, not for billions of years, but eventually the universe will become uninhabitable and unobservable. The Great Attractor also reveals something about the universe's large-scale uniformity. Despite being a massive structure, despite pulling on galaxies across hundreds of millions of light years, it's not unique. Other basins of attraction exist throughout the universe. Shapley sits beyond the Great Attractor, the Perseus Pisces supercluster sits in another direction. The Hercules supercluster sits in yet another direction. These structures are all comparable in size and mass. The universe is lumpy on small scales, but smooth when you average over large enough regions. This confirms the cosmological principle, the idea that the universe looks roughly the same from any location. If the Great Attractor were a unique feature, if our region of space were dramatically different from other regions, cosmological models would need revision. Instead, the Great Attractor appears to be a typical example of the largest structures that gravity can build. Its existence fits predictions. Its properties match simulations. It's exactly what you'd expect to find in a universe governed by gravity and dark energy starting from nearly uniform initial conditions. Yet mysteries remain. The structures we observe are slightly larger than theoretical predictions suggest should be possible. The time since the Big Bang seems barely sufficient for gravity to organize matter on such enormous scales. Either something about the early universe was different than currently modeled, or the models themselves need adjustment. The Great Attractor and structures like it sit right at the edge of theoretical expectations, challenging our understanding while also confirming basic principles. The ultimate fate of the universe is written in equations describing dark energy and cosmic expansion. If dark energy remains constant, expansion will accelerate forever. If dark energy grows stronger with time, expansion will accelerate even faster, eventually tearing apart even atoms in a big rip. If dark energy weakens, gravity might eventually overcome it, causing the universe to collapse in a big crunch. Current observations favor eternal expansion, but uncertainties remain. What we know for certain is that the Great Attractor's pull, as strong as it is, as massive as the structures generating it are, will eventually lose its battle against dark energy. The expansion of space will win. The cosmic web will tear apart. And in the far future, when the last stars have burned out and the last black holes have evaporated, nothing will remain but cold, dark, empty space expanding forever into an infinite void. After decades of research, after mapping millions of galaxies, after tracing cosmic flows across 1 billion light-years, we've answered some questions about the Great Attractor. We know roughly where it is. We know roughly what generates its gravitational pull. We know it's part of larger structures extending across cosmic scales, but vast regions remain unmapped. Critical questions remain unanswered. The frontier of knowledge keeps expanding, revealing new mysteries as fast as we solve old ones. 20% of the sky remains hidden behind the zone of avoidance. We've pierced this veil with radio and infrared observations, but incompletely. The densest regions of galactic dust still block our view. The brightest regions of foreground stars still interfere with detecting faint background galaxies. We've found major structures like the Norma cluster, but smaller structures remain invisible. We've mapped the rough outline, but lack detailed knowledge of exactly what hides in that zone. Beyond 1 billion light-years, our maps become sparse and uncertain. We've detected galaxies at these distances. We've measured their approximate positions. But precise distance estimates require techniques that don't work well for faint, distant objects. Peculiar velocities become impossible to measure when redshift from cosmic expansion dominates. We can see that galaxies exist out there, but we cannot reliably determine how they're moving or what larger structures they belong to. The southern sky has been surveyed less thoroughly than the northern sky, Most major observatories sit in the northern hemisphere, where more people live and more funding concentrates. The southern sky contains unique structures like the South Pole Wall that remained hidden simply because fewer telescopes observed that region carefully. As new observatories come online in the southern hemisphere, as existing surveys expand southward coverage, more discoveries will emerge. Dark matter's distribution remains poorly mapped. We know it dominates the mass. We know it forms halos around galaxies and clusters. We know it creates the gravitational scaffolding for visible structures, but we cannot observe it directly. Every measurement of dark matter distribution is indirect, inferred from gravitational effects on visible matter or from gravitational lensing of background light. The precision of these measurements is limited. The uncertainties are large. We have a rough picture of where dark matter concentrates, but the detailed structure remains unknown. The exact relationship between Laniakea and Shapley needs clarification. Is Laniakea a separate supercluster falling towards Shapley, or is it a sub-basin within Shapley's larger basin of attraction? Different analyses using different methodologies give different answers. The distinction matters because it determines how we define superclusters and how we understand the hierarchy of cosmic structure. But resolving the question requires better data, more precise velocity measurements, more complete mapping of distant galaxies. We don't understand why the largest structures are as large as they are. The Great Wall, the Sloan, Great Wall, the South Pole Wall, all exceed the theoretical size limits for structures that could form in the time available since the Big Bang. Either the initial density fluctuations were larger than models predict, or structure formation proceeded faster than expected, or some mechanism we don't understand concentrated matter more efficiently than gravity alone should allow. The observations are solid. The structures exist, but the theory doesn't fully explain them. Dark energy's nature remains mysterious. We know it exists. We know it drives cosmic expansion. We know it will eventually overcome gravity and tear apart the cosmic web. But we don't know what it is, where it comes from, why it has the value it does, or whether it's truly constant over time. If dark energy changes, everything we predict about the universe's fate could be wrong. The Great Attractor might remain influential longer than expected, or lose its influence faster. Structures might grow larger or disperse sooner. The timeline of cosmic evolution depends critically on understanding dark energy. Future surveys will map the universe in unprecedented detail. The Vera Rubin Observatory will photograph the entire southern sky every few nights, detecting billions of galaxies and mapping how their positions change over time. The Euclid Space Telescope will map galaxy positions and shapes across much of the sky, measuring gravitational lensing to reveal dark matter distribution. The Nancy Grace Roman Space Telescope will conduct surveys of distant galaxies to trace large-scale structure deep into cosmic history. Each of these missions will discover new structures, reveal hidden patterns, and raise new questions. But some questions might remain forever unanswered. The zone of avoidance, no matter how advanced our technology becomes, will always block part of our view. Some wavelengths simply cannot penetrate the thickest galactic dust. Regions beyond our cosmic horizon will remain forever invisible because their light will never reach us. The universe is larger than we can observe, more complex than we can fully map, more mysterious than we can completely understand. And perhaps that's how it should be. The Great Attractor pulled us across the cosmos for billions of years before we even knew it existed. It shaped our galaxy's path through space, determined where we're going, influenced our cosmic destiny. We've spent decades studying it, mapping it, trying to understand it. We've learned much, but mysteries remain. the frontier continues expanding. The universe keeps revealing new depths of complexity. We're explorers in a cosmic ocean, charting waters we can barely see, following currents we don't fully understand, pulled by forces we cannot resist. The Great Attractor is real. Its influence is real. But 20% of the sky remains unseen. Billions of light years remain unmapped. The universe's largest structures challenge our theories. Dark matter and dark energy remain mysterious. The journey continues. The questions multiply. And somewhere out there, in the darkness beyond our current knowledge, more wonders wait to be discovered. The Great Attractor pulls us still. The journey is far from over. And the greatest mysteries might lie not in what we've found, but in what we haven't yet discovered in the vast darkness that remains unexplored.